Most people picture a tsunami as a towering wall of water. That image is real, the devastation is real. But the wall of water is the last thing that happens, not the first. The process started hours earlier, far beneath the ocean's surface. And it begins with something that has nothing to do with water. To understand a tsunami, you have to go underground. The ocean floor isn't a flat, featureless plain. It's covered in mountains, trenches, and vast sediment plains. And at its edges, where ocean meets continent, something extraordinary is constantly happening. This edge is where almost every major tsunami in history has started. At the ocean's edges, two giant slabs of rock are in a slow, merciless collision. The oceanic slab is denser and heavier than the continental slab. So the oceanic slab loses. It begins to sink, slowly diving beneath the other plate down into the earth. This is called a subduction zone. It happens along thousands of kilometers of coastline, around the Pacific Ocean alone. Japan, Indonesia, Chile, Alaska, the Pacific Northwest. All of these coasts are positioned directly above subduction zones. The two plates don't slide smoothly. The boundary between them, the fault, locks together under enormous pressure. Friction holds them stuck. But the underlying movement of the plates doesn't stop. It continues, millimeter by millimeter, year after year, decade after decade. The overriding plate slowly bends and stretches, dragged downward by the sinking slab. Stress accumulates in the rock, the way it builds in a spring you keep compressing. This can go on for decades, or for centuries. GPS networks today can measure this deformation directly. The land is visibly bending and compressing by centimeters every year. You can watch the spring being loaded in real time. Eventually, the stored tension exceeds the friction. The locked fault snaps. The break races along the fault line at 2 to 3 kilometers per second. The overriding plate, which had been bent downward, springs back upward. In 2004, this process ran for nearly 10 minutes. The rupture traveled 1,200 kilometers, roughly the distance from London to Athens. A section of ocean floor, roughly the size of Iceland, rose by 5 to 10 meters. In under 10 minutes. This is a megathrust earthquake. And what makes it a tsunami generator isn't the shaking. It's that vertical movement, the seafloor actually rising. When that much seafloor rises that fast, the entire water column above it moves. Not just the surface. The full depth, from the seafloor kilometers down to the surface, moves. Water can't compress, so it has to go somewhere. The displaced water radiates outward, in every direction. The ocean rings, like a bell struck from below. The energy loaded into that wave in 2004. Equivalent to roughly 1,000 Hiroshima bombs. You'd expect to see it coming. But in the open ocean, the 2004 tsunami was 60 centimeters high. The wave that killed 228,000 people. Ships passing over it felt nothing. The energy was entirely invisible, spread thin across hundreds of kilometers. A tsunami isn't a tall wave. It's an incredibly long, thin disturbance, moving through the full depth of the ocean. A tsunami's speed depends on water depth, not on wave height. The deeper the water, the faster the wave travels. In 4,000 meters of water, it travels at about 700 kilometers an hour, the speed of a commercial jet. The 2004 tsunami crossed the Indian Ocean in under 8 hours. That 700-kilometer speed is a little misleading, though. What travels at 700 kilometers an hour isn't water. It's the disturbance, the pressure pulse, moving through the water column. The actual water particles barely move while the wave passes. Think of a wave traveling down a rope. The rope itself doesn't travel, the disturbance does. A tsunami in the open ocean works the same way, at continental scale. Everything changes as the tsunami approaches a coastline. As water gets shallower, the wave slows down. but it still carries the same energy. When speed drops, that energy has to go somewhere, and it goes upward. Wave height increases as the wave is forced into a smaller and smaller volume of water. A wave that was 60 centimeters in the deep ocean can reach 10 or 20 meters near shore. In some locations, with the right coastal shape, it can reach 30 or 40 meters. That's taller than a 12-story building. Bays and inlets act like funnels, concentrating energy into a narrower and narrower space. Two harbors side by side can experience entirely different wave heights from the same tsunami. You've probably heard that the sea retreating before a tsunami is a warning sign. It can be, but most people misunderstand what it means. The sea retreating isn't a sign that the tsunami is coming. The retreating water is the tsunami. It's the low point of the wave, the trough, arriving before the crest. A tsunami isn't a single wave. It's a wave train, crests and troughs arriving one after the other. Which part reaches you first depends on which side of the rupture you're on. On one side, the crest arrives first. Water rises immediately with no warning. On the other, the trough arrives first, and the sea goes out dramatically. In 2004, people in Thailand watched the sea retreat and walked onto the exposed seafloor. They were walking toward the crest. The 2004 disaster revealed something the world had overlooked. The Indian Ocean had no tsunami warning system at all. Even Japan, which had the most advanced system in the world, underestimated the 2011 tsunami. The system predicted a 6-meter wave. The actual wave reached 40 meters in some places. The earthquake was larger than anything the algorithm had been designed for. Japan's response: when you feel strong shaking near the coast, run uphill immediately. Don't wait for the official warning. Not all earthquakes that trigger tsunamis shake the coast violently. Some ruptures spread slowly, almost silently, from an earthquake sensor's point of view. Coastal residents feel mild tremors and have no reason to evacuate. Minutes later, a wave arrives that's completely out of proportion to the shaking. These are called tsunami earthquakes, and they're the hardest to detect in advance. Warning systems that rely on shaking intensity alone will miss them entirely. The coastline looks exactly like it always did. But now, you know it's the last act of something that began centuries ago, in rock. Every one of these locked fault boundaries in the world is under strain, right now. All of them are building. The next tsunami isn't a question of chance. It's a question of time. See you next time.